Okay, great. Hello, everyone. Today we are going to discuss chapter 11 for designing data intensive application, which is stream processing. And today Shreya is going to present that. So, Shreya, you can start it. Shreya, no, I cannot hear you.
Hello.
Yeah, I can hear you now. Shreya, I think you are mute. You need to unmute yourself.
Yeah, I unmuted. Can you hear me now?
Yeah, I can hear you fine.
Okay. Hello, can everyone see my screen?
Yes, I
We
can.
can see it.
Yeah, so today's chapter that we are going to talk about is stream processing. And in stream processing, the author starts by explaining the need for stream processing. So, why do we need stream processing? Uh, so, the author says that when we were doing batch processing, at that time when we were curating the information, we were waiting basically for the bulk of data to be there for some time. Sometimes the result comes after one day. The result might come after 1 hour as well. So basically, you have to wait for a certain amount of time in order to perform the aggregation on top of that bulk of data. But in stream processing, you don't have to wait for that results to get produced. You can get results immediately. So wherever you want to get results in real time, you would want to consider stream processing as the option solution. So what are the possible options for stream processing? Like how can you create those stream processing, what is inside those streams, right? So those streams are nothing but what it was there in bad jobs. Like in bad jobs you have events of data produced by your user, right, on which you perform operations. In stream processing also you just have events, and then whatever events gets generated, you transmit those events, and then the complete event set, those streams are getting generated. And once those are generated, you might want to do certain things on top of it, like uh, some people might want to create alerting on it for services, or you might want to have like two systems in sync. Then you would want stream processing. So in certain cases, stream processing comes handy, and it has messages in it which helps, which are events, which gets transmitted between systems. Now, these transmitting events, how can we do that? We can do that with something called as message systems. So message systems are like when how you can talk with each other, how messages can be transmitted from one system to another. So their message systems are there. So you can have your own message system where you have a producer and you have a consumer. For example, something like, uh, directly producer can talk to consumer, and you don't have anything in the middle. Here producer is producing and consumer is consuming, and these messages are directly transmitting from producer to consumer. Now here what will happen is my application needs to take care of everything, because the producer also I have written, uh, and the consumer also, I have to take care of if the consumer has received a message, or if I have written consumer, then I have to take care everything about what consumer needs to do, right? So in that cases, what could be the issues, right? Uh, s- so first of all, how can you make these basic communication? One of the way is you can make it through TCP uh, protocol. The other one you can do is with UDP. Okay. The next case that you could use is like Unix pipes or something like that. Uh, so all these messaging system basically depends on like TCP or Unix pipe, and they start building up from there. So, but any this producer consumer model, basically this is publisher, if we call it, and this is subscriber. So this consumer has subscribed to this publisher events, and then these events will be given to these consumers. So in such cases, there are certain questions. What happens if the producer send messages faster than the consumer can process them? So what are the options for you? So now producer is transmitting messages at 4 times rate, but consumer is consuming only at the rate of 1. So how what will happen after a certain time? The consumer will not be able to accept those messages. So you have first option to either drop the message that are coming. Second option is that you put it in a queue, right? So that message gets buffered in it. And third option is back pressure. So back pressure is when you don't basically you don't accept the messages from producer anymore. So this analogy can work with like how USPS works, right? uh, Basically, they have these mails and they have to send it to people, and when they have a lot of emails, they can put it in a queue, and then they can and then they will send it to you, right? And it can take their own they can take their own time on when they want to their like their standard delivery time, right? In that much time they will just send you the messages. Actually, sorry, I said something wrong over here. So yeah, USPS analogy will be only for like the queue. So whatever emails you have to get, they'll start sending you. And if you're not available, they will be basically get putting it as a queue in front of your door or in your mailbox. So that's the queue analogy there. And for and then back pressure is when you don't basically uh, are available and you don't accept any messages from the producer. So that's back pressure. So these are the three things that you do when the messages are producing faster than the consumer. And what happens if any of the nodes crashes? So if producer crashes, then your messages are lost. So whatever messages are there on the producer side, if it is supposed to produce, like for example these 1 2 3 messages, and if producer is crashed, then you will lose these messages until you persist it in the hard disk. Then second thing is message can get lost in the network. So for that you can implement a acknowledgement system where whenever consumer receives a message, it gets acknowledged. It sends acknowledgement to the producer so that now producer can understand that messages received on the consumer side or not. And the next case is consumer can crash. When consumer crash, again there will be no acknowledgement, so producer can retry and send it to the consumer. So these are the cases and how you can follow them. Now there are two ways to do messaging. First,
We're talking about direct sending of messages, or we have some queue in between to send the messages.
right now I was talking about any general message system. Like,
Okay.
yeah. So let's assume this is the first one. Like there is direct communication and no queue, nothing in the middle. But basically no intermediary node in the middle. You can have a queue, but not as an intermediary node, but as part of consumer. So like this queue will be part of the consumer service.
Okay, consumer will have a queue. Okay.
Yeah, consumer will have a queue, because here I'm explaining, basically I was talking more in perspective of direct communication, where producer can directly talk to consumer and not have to go through a node.
Okay, so to buffer the messages, consumer will have a queue so that it can keep those messages. Okay. Yeah.
Yeah, you can keep those messages.
Yeah, it's like it have like a RPC, right? Remote call. But even with the queue, the consumer keep the message, but before they keep the message, I have to send the acknowledge to the producer first, right?
Yeah, but I was thinking if it does that, and if consumer crashes, the queue might get lost. Then the message is lost basically, and producer has now received a wrong acknowledgement.
So
So
you,
yeah,
okay.
go ahead.
So are you saying just don't send the acknowledge to the producer, just keep queuing them? Then on the other side of the queue, when the process and it send the acknowledge to the consumer.
Yeah, maybe. But again, I was thinking then if that's the case, and if there is a long running message on consumer, and if this message one is getting stuck over here for a long period of time, producer might produce number like this message one, it might retry again and again, and then
Yeah, that's a
so
problem. Huh?
that's a problem. Yeah.
Yeah.
So I'm not really sure like exactly when it sends acknowledgement over here,
Okay.
because in both the cases there is either of one or the other problem, right?
Right. Yeah.
Yeah. So yeah, for that there is a solution, but let's first talk about all the problems in this direct communication, and then we'll come to know like how this problem can be solved. Okay, so the next thing in direct communication, like there are two ways of doing messaging, right? One is direct messaging from producer to consumer, and another one is message broker. So let's talk about direct messaging from producer to consumer. So in direct, a message from producer or consumer, you can, as I told, you can implement it through TCP, UDP. You can implement through REST calls if they have exposed API, or you can have remote procedure calls, right? Now, once you have implemented this system, one advantage or pros of the system is that the latency will be really low. How can we understand that is if, for example, I have to deliver a package to one of my friends, I can just take my car and go to his or her place and then deliver it, right? But if I choose to go through USPS, then USPS will take its standard time to deliver the message. So that's why I said that it will be much faster if we go and deliver. So here producer is just going and delivering directly to consumer without a node in the middle or without any system, intermediate system in the middle. So the latency is really low. But with it there will be a lot of hassle, right? Because you have to make sure of everything, that it's durable, and you have to make it fault tolerant and scalable at like everything. Because as you can see in this case, producer was producing at 4 times but consumer was consuming at one time only. So you might want to scale your consumers here. So all these things you will have to take care of. So there are different systems which helps you do that. These kinds of systems, this direct communication system, are used in financial sector, in stock markets, because they really require low latency. So they actually build such kind of systems. But in general, like there are something called as message broker. And what message broker does is it makes producer and consumer independent. So now producer and consumer are independent systems. And there is this message broker in the middle. And what producer will do?
We can see it. Are you drawing something?
Yeah, I'm drawing. Can you not see?
No, because I think you have only shared your Notion.
Oh, I have been drawing from a long time. Sorry.
So you need to stop sharing only application, then you should probably share your screen.
So can you see now?
Yeah.
Oh yeah, I have. Okay, let me draw again. So so in direct communication there is publisher and there is subscriber, and they can talk directly with each other. So this is like message and this is acknowledgement. So basically this is what the communication looks like. It can be done through TCP, UDP, REST calls, or RPC, right? And then there will be a message broker. In message broker, there will be producer, consumer, and the message broker will be in the middle. So now it's message broker's responsibility that whenever a message is produced, it stores that message and it tells producer, okay, and now you can go ahead produce more messages. I have stored your message. And consumer can consume on its own rate. And if needed, then message broker can attach more consumers to it. And if needed, it can attach more producers to it. So like the scalability is now on message broker. You just have to have these producer clients. So basically these will be clients and consumer clients. You have to just implement those, and message broker will take care of storing the message, scaling, and durability of your system, so that message is sent from producer to consumer. So now someone asked this question, right? Like, when do we understand the messages process? When do we send an acknowledgement? So now you see that acknowledgement is sent here, right? From message broker to producer, and consumer can consume on its own rate now. And we don't have to deal with that whole problem that when should we actually send acknowledgement in order to understand that the message is being processed.
Yeah, also like I was talking about retry logic. So if like to your USPS analogy, if I have to directly send the message, if I have to directly send the packet to my friend, then I have to take care of retrying that. If my friend is not available, I would have to go and drive to his house again, probably 3-4 times until he's available and he can take my message. Whereas if I go to USPS, I can just drop the message at them and then I'm done. Now it's the responsibility of USPS to keep on retrying if my friend is available or not, right? So retrying is also another benefit of these
Yeah,
messaging.
absolutely. It's the correct analogy. Yeah. So that's what going to happen at message broker. Okay. Now, in message broker, yeah, this was the how the system would look like. Okay. And message broker are also known as widely known as messaging queue, right? And they have certain advantages, that producer and consumers are independent, that we talked about, and durability is now like message broker's headache. You don't have to worry about it. Yeah, and another advantage is there is uh, unbounded queue. So like in this situation, right, when the queue was part of the consumer, you have some length of queue, right? And after that you will have to apply back pressure. You cannot accept more messages, or you will have to drop the messages, right? So in such so you have a bounded queue, whereas in message broker you have an unbounded queue. So there is unbounded queue. So the queue will be limited by the disk space of the system, and if needed, you can just partition the logs and then add more of these to make that like one system. So this is unbounded queue. So this is another advantage to it. Then these message broker, they do look like databases. So how are they similar, or how are they different with databases? So in databases, you usually keep the data until it is explicitly deleted. So until unless a user goes and write the query that you delete this message, um, delete something or a certain row, nobody else is going to delete it. But in what happens in message brokers is, once the message is successfully delivered to the consumer, that consumer has consumed the message, then it will be automatically deleted from the queue of this message broker. Okay. uh, and message brokers are assumed to have like short-lived data, short data. They're not suitable for long-term data storage. Then databases often support this search queries, uh, and in the similar way, message brokers have a way of subscribing to topics. We'll come to what topics is, but you can understand it's a way of subscribing to the interested messages you are in. Like, for example, you might be interested in some notifications about weather. You can subscribe to that, and you will get notifications anytime the weather changes or something happens. Okay, so that's there. And then the other one is in a database. The result is typically based on. Okay, so yeah, what happens in a database is like, if I go and query the value, say for example there was some value X in the database, And if I go and query this value, it will be 3. And now when somebody comes and updates it to 4, I will not know until and unless I go and explicitly go and check it again, that what's the value of X. But what happens in message broker is that if the value is changed from 3 to 4, I will be notified that this value is changed. So that's the difference. So that was the differences about message broker versus database that book talked about. Now, how can systems with multiple consumer be implemented? Like, how can you implement a system, a message broker system where there are multiple consumers? So there are certain ways. If we can see, I hope everyone can see my screen. There is this figure from the book which specifies 2 ways: load balancing and fan out. So what happens in load balancing is, as the name suggests, the load is balancing. So producers are producing messages in the broker, and now this broker is distributing load among different consumers. So as you can see here, the message 1 is getting delivered to consumer 2, and message 2 here is getting delivered to consumer 1, and message 3 is getting delivered to consumer 2, and message 4 is getting delivered to consumer 1. So they basically divided the load. They basically might have hashed messages in order to understand which consumer should get that message, or they might be just doing some load balancing algorithm around robin, or to alternate the messages among different consumers, right? Now, the other option is fan out. The fan out is when you broadcast all the messages to all the consumers. So, as you can see in the diagram B, M1, M2, M3, M4, M5 is broadcast to consumer 1 and consumer 2 both. So, this is the fan out approach. We can think about fan out approach. For example, in load balancing, where would be we would be using this approach is where you have 4 machines that can consume, or 4 nodes that can consume, and then you can just distribute the load, and you are okay to get the messages, without in, like, it doesn't matter what the order is. So when what from consumer 1 you can get M2, M4, and consumer 2 you can get M1, M3. So even if, like, message 2 is received before message 1, it doesn't matter. You can consume them, and you can distribute the load. But when you are using fan out, you can preserve the load, and this could be used in cases where um, you have to have these search queries, and these search queries needs to go in all the places to search the data. In such cases you can use fan out. Then there is something called as hybrid, which is the mix of these two approaches. You can use it in a way that these group of consumers can receive all messages first. So first fan out is implemented, and then inside this fan out, only one of the node, basically if you have messages being sent to consumer 1, consumer 2, and consumer 3. So in this case, they could be like, really a group of multiple consumers here. Like within consumer, there is a group of consumer. So this message 1 is transmitted to all the 3 consumer groups. And then within these consumer groups, uh, this message 1 is transferred only to, let's say, this one. And message is transferred to only this one. And this is transferred to some over here, C3 dash dash.
So load balancing is like partitioning your messages, that overall whatever load of messages you have partitioned it among consumer 1 and consumer 2. So some messages will be received by consumer 1 and some will be received by consumer 2. Fan out is kind of replication, where all these messages are replicated to all the nodes. So exactly same set of messages both consumer 1 will have and consumer 2 will have. So if like multiple consumers are interested in same messages, they're independent of each other, they all want the messages, then we will use fan out kind of a system. Or if you want to keep a replication of your messages, then you will use a fan out. Whereas load balancing, I see that when you have like the load is very high, like there are a lot of messages to be processed, and one machine cannot process that much amount of machine. So you will set up multiple consumers which will load balance the messages. So some consumers will take some messages, right? And so that's how you're partitioning your overall load among multiple consumers.
Yes.
So in the fan out, like does it the total order or the message is being maintained by the broker, or like the message could be arrive in random order?
I
So
believe the order should be preserved.
preserved, yeah.
Yeah, it will keep on retrying, so it will have the logic. The broker will have the logic that uh, this message I have delivered to this consumer, and it is still pending to be delivered to this consumer. So it will keep the message until it has delivered to all the consumers. Once it has delivered to all the consumers, then it will delete the message, and it should be keep on retrying it. So
So total order broadcast, right? It will
Yeah, right.
depend, I think, on load balancing fan out, and we'll come to that in the next topic. That in load balancing, you cannot have total order broadcast. In fan out, there will be, because yeah, that is basically you're broadcasting the messages, so all will be in the same order.
Okay.
So like in here, this is the one diagram, like where in acknowledgement and delivery you'll see like how order is there and not there. So for example, here they have shown it as a partitioned or basically load balancing way of implementing multiple consumers. And here producer 1 have and producer 2 have produced the messages, and broker has now M1, M2, M3, M4, M5 messages. Now M1 is delivered to consumer 2 and M2 is delivered to consumer 1, and M3 is delivered to consumer 2, and when M3 got delivered, consumer 2 crashed. So there was no acknowledgement related to M3 that was received by broker. So what a broker will do is now broker will retry M3 again. So when broker will retry M3, before M3 could reach to consumer 1, M4 was already delivered to consumer 1, and then M3 was delivered, and the system continued. Now there was no error because obviously there is nobody knows what the order is, but here now order is actually changed. It has changed from M1, M2, M3, M4, M5 to M1, M2, M4, M3, and M5. So they said whenever you have to maintain the order, then don't use load balancer, or you should make sure that your request always goes to the same consumer whenever it was requested. Like certain messages, if they are part, they went to consumer 1 and the next ordered message should go to consumer 1, it should go to consumer 1, it cannot go to consumer 2. Either you have to make sure of that. So in acknowledgement and redelivery, this could be the problem in partition logs or the load balancing one. So now next up, the topic is partition logs. And in partition logs, we are going to talk
I
about.
had a one question. Is it
Yeah.
okay? Like, how do we know if we want to deliver to M1 to two consumers, right? How it will be delivered?
So how it will be delivered? First of all, the consumers will subscribe to this broker. So basically, consumer 1 and consumer 2 will be part of one consumer group, because and then consumer 1 and consumer 2 will tell that I am interested in these messages, please deliver it to me. And then broker will can probably hash out the message and decide on which one it should deliver. So this basically comes into what load balancing algorithm you're using in order to know which message to deliver to which consumer.
So your question is load balancing or fan out, that we have to send the message to both the nodes?
I think it will come on the fan out, I think, right? Yeah.
Okay, so so the question is that it has to deliver to both. It's fan out.
Okay, so in that case, like that's the implementation technology. So, like the way how you want to implement consumers in your system. So, whenever you are going to have multiple consumers, so you'll have a consumer client. Then in that consumer client, you can have consumer group. That these are my group of consumers, and all needs to have these messages, right? Or there could be like a subscription kind of thing, that where multiple services are there independent, but they have all subscribed to this broker, that I'm interested in these messages. So then broker will know that okay, these messages are needs to be delivered to this consumer client, and then consumer client will uh, send messages to all those consumers. Does it make sense?
Yeah, yeah. Okay. Yeah.
So next up is partition logs. In partition logs, we have already talked about this briefly, that once the messages are consumed, they will be deleted. And this is called transient messaging mindset, that whenever the messages are consumed by consumer, then the messages will be deleted as soon as it is consumed. So in cases like if you want to add a new consumer, when some of the messages have already been consumed, you cannot make that consumer come to a place where all other consumers are. So for example, there was some system where there were certain messages, uh, and there was consumer one which was consuming this message. Now we wanted, okay, my consumer one was not able to get all, like my consumer one was not enough, so I want to put consumer 2 also. And then when I add consumer 2, the the problem is that now, because these messages were deleted, like the past messages were deleted, in order to make consumer 2 equivalent to consumer 1, I can't do anything about it because messages are already deleted. So I'll need this consumer 2 will start working only from the time that you have added it. So it will start consuming from there. So its state will be different than that of consumer 1. Um, that's what partition log is. So what we can do about it is, like there are systems which are created with logs. Instead of just adding messages in the queue and deleting them, you can store these messages like further. Like if some consumer gets added in the future, though, you can replay those messages and you can bring those consumers also to the same state of the previous consumers. So that brings us to the solution of logs for message storage. So this is like and the example of it is like Apache Kafka, where you have logs instead of uh, just messages being there and then getting deleted. So this would be the ideal system that looks like. So here what happens is the log. So if we see here this topic A, so the topic is anything that consumer is interested in, and consumer subscribes to the topic. Okay. You can understand it as the same thing like weather. If you are interested in the notification, whenever the weather change, you will get a notification about it. So, and topic can be is basically the same type of messages will be grouped under one topic. So here, partition 0 and partition 1 have similar type of messages. So they are grouped under topic A. And here partition 0, partition 1, and partition 2 are grouped under topic B. That means these partitions have a different type, like same type of messages but different than the topic A messages. So that's the concept of topic. Now what happens is whenever a message comes, it gets appended in the end. So as you can see in topic A, partition 0, the producer is appending the message at the end, right? And consumer starts reading from the start. So if you can see topic A, partition 0, the consumer will start reading from 1, or and it will read sequentially. Another thing that happens when these messages are getting created and getting appended as a log is message broker will assign a number to them, that okay, this was message 1, this is message 2, and this will be a monotonically increasing number, like first message will get number 1, second message will get number 2, and so on. And there is no guarantee between the partitions, like in partition 0 and partition 1 we cannot guarantee the order, but in partition 0, if message is getting consumed by one consumer, we can guarantee the order, that whatever is consumed from partition 0 will preserve the order. So this is what logs log system, log message broker will look like as compared to the traditional message broker we have been talking about up till now. So how are these different? The log messaging, yes.
I was asking, so this system will not delete the messages? Like, is it to solve the problem that
Yes.
consumer 2, if it is added, it cannot read the message from history because they have been deleted? So
Yes.
we implemented the system so we can solve that problem, or
Yeah, that problem. So we are not deleting any messages. So the problem was that for example, you can understand it a way, right? If there was leader and follower, right? You can understand that leader and follower are there, and leader was consuming from some message broker and follower was also consuming from a message broker, and a new follower came, right? And then how will we let that follower catch up if we don't have the possibility that we can get it catched up with the leader? So that will not be the scenario in general, but I'm just saying that, for example, we don't have this option where follower can catch up with the leader. Like follower can ask leader, like, give me all those things that have happened up till now in the system. And we had this option of message broker. So in that case, message broker will not be able to help because messages are already deleted, which are consumed by this leader. So in such a case, now we want these two systems to bring in sync. So our ideal approach would be, if I don't delete those messages, then what I can do is I can replay those messages on this follower, and that follower will also have like the same state as the leader. So in order to solve that problem, what they're doing is they're preserving those messages. Preserving as in they're just storing it and will not delete it.
so remember initially we were discussing difference between database and message system. So we were saying that the difference is that message systems delete the message,
Mhm.
whereas databases keep the message, right?
Yeah.
So if you are building this log-based messaging queuing system, then it is more closer to databases because now we are also not deleting the messages in them, right?
Yeah, in fact, in the book, they talk about it like if further that how these systems have learned from each other. Like the message broker have taken this property of databases to store the data, to persist the data for longer period of time, and how database have learned certain properties from message broker. And we'll come to that, like what properties database has learned. But yeah, there are things that systems have learned also from each other.
And so then,
Yeah.
yeah, yeah, go ahead.
In the point of another one is the scalability, right? When it reaches a more size, how it will be consumer will know to reach out to the proper partition.
Yeah.
Number 4, yeah.
Yeah, I said about that monotonically increasing sequence, right? That message broker provides. So consumer over here has an offset called consumer offset. So for example, you can see inside this consumer client, consumer group, there is consumer client, and offset for b dot 0 is equal to 4. Is that means consumer client has read up till 4, and the next it will read is from 5.
So this offset has to be kept by consumer or by the topic.
So the consumer offset is a property of consumer. Consumer will keep it, and message broker will also have this information, but like not like every time, but they will sync up with each other periodically.
Okay. So each consumer knows that up till what index it has read the message, so that it can continue reading from there.
The next, yes.
Actually, in reality, the consumer offset is stored with a distributed system like Zookeeper.
Oh, nice to
Yeah.
know. Mhm. Yeah, and that makes sense, right? Because if further in the chapter, we'll read about it. What's the use of it? Like, why do we want to keep consumer offset at a place, at a centralized place, or a place where consumer don't lose it or message broker don't lose it?
Yeah, and in case of such message broker, what we use, load balancing or fan out? What do we use? Load balancing or fan out when we consume message from Kafka-like system?
Oh, okay. So yeah, here, as you can see, this is so what happens is partition can be assigned to a consumer group. That like one consumer node you can assign to a partition. So that's more about configuration. For example, here partition 0 is assigned to consumer client, the first one, and partition 1 is also assigned to the consumer client, but partition 2 is assigned to the second consumer client. So this looks like more of load balancing,
Yeah,
right?
but I still have possibility to read the same message by different consumer, yeah?
Yes. So yeah, both are implementation ways of message broker. You can implement in both ways.
Yeah, so it look like hybrid approach, no?
Yeah, it's possible.
Okay, thank you.
Yeah, but one more point that I remembered is that you cannot have like more consumers than partition. For example, here you have 3 partitions, right? So you can have at most 3 consumers and not more than that.
Actually, you can have more consumers, but it's just that the other consumer will just wait and will not consume because there are not enough partitions to consume.
Consume, yeah. So they in here they have mentioned that that the number of consumer client cannot be more than the partition, because I thought it is because of order. So are you saying that it can, but it will not just consume? It's
Yeah,
just wastage. Okay.
yeah, it will just waste.
Cannot be more because like others have to wait. So it is equivalent to like not having more, right? Because others are waiting, so they are not part of the system.
Yeah, correct.
Why we need that restriction?
Because then how will the two consumers, so let's say then two consumers will have to read from the same partition, right? Because like we have more consumers than the number of partitions. So the advantage of having less consumers is like they are reading from different partitions. But now if we have more consumers, then multiple consumers would have to read from same partition. And then so, and I think because this scenario is load balancing, so then it will be hard to keep synchronization between which consumer has read up till which index in that partition. So it will be hard to coordinate between those two consumers. So that's why they are keeping. Am I right, or is there any other reason?
Yeah, inside a consumer group, one consumer can uh, read from one partition at least. It can read from more than one, but at most it can read from one partition. So let's suppose you have a consumer group called C, right? And inside that you have a topic which has 10 partitions. So either you can have one consumer consuming from those 10 partitions alone, or you can have 10 consumers consuming from each partitions. So that will mean that one consumer is consuming from each partition. So 10 into 1 is equal to like 10 partitions. So in case you have 12 consumers, right? So since one consumer can consume one partition, then the other two consumers will just wait. They'll not be able to consume.
Yeah.
Yeah, but I'm asking why we have that restriction. Why would it have to be 1-to-1? I mean, like, let's say we do like the previous way up, before the previous slide, we have like a broker message, right? And a broker message can have one producer but multiple consumer, right?
But
So in this case,
what's the advantage of one consumer consuming from, sorry,
so
two
like for
consuming from?
example, you have a message in the queue. One message could take a long time to process. Why waiting, right? To deliver it one by one. Why not, one consumer process this message, and then while you process, the other consumer can pick the next message to process it.
But how will they have to coordinate with each other, right? So let's say there is two consumers who are reading from the same partition 0, right? So now consumer 1 has read the first message. How will consumer 2 know that now it has to read the second message, because first message has already been read by his other partner?
There's
If
visibility, right? The consumer one take the message, the visibility of that message is, become hidden for certain amount of time. Then, consumer 2 come and then pick up the second one. They depend on the consumer business logic, whether the consumer decide to process, message in the order one by one, or, it can process the message in any order.
So that's the property of message broker, right? If you're hiding the message, that's something which is implemented in message broker. You can't do anything about it, right? So in the previous solutions, you were able to consume with multiple consumers because as soon as the message was consumed, the message was deleted. So there was no coordination needed. But in this case, we are not deleting the message. Now you said for certain time you need to hide the message. That code will have to be implemented in message broker, and this message broker, we are not implementing it, right? And the whole point of why we don't want it to hide is, if some, let's say some consumer was getting added newly, and then it wanted to catch up, it might even miss that message because that message was hidden for certain time from consumer.
And also the one implementation reason of that was, if we take, like, for example, what Leon is saying, like there are two consumers who are reading from the same partition. So even if their processing time is more, they can alternatively check out the messages from the partition and consume it faster. The one important reason for these people to implement these log messages was, you need a very high throughput, and you want to guarantee a very low latency, as well as a very fast response time. So the way, if you look at these messages, like there are no random reads happening. Like everything is writing is all sequential, and reading is also all sequential. So when you read sequentially, the speed of the disks, and because Kafka is not keeping them all these messages into the memory, because it persists into the disk. And if you are tailing to a disk, basically I'm saying, like, if you are doing a sequential read, it is like 100 300 times faster than doing a random write. So to avoid that, they have put a restriction on this design, that only one client will read, so that he will see a sequence, he will be reading it sequentially instead of doing a hop on hop off kind of a thing. So I think that is the one. But the question is still the same, right? What if the consumer is taking time? So
Mm-hmm.
if so, for that there are other options, like, um, I think one option is do a batching, like check out a bunch of batch messages and use spin out an internal threads for handling those messages, and then all the work is happening in parallel. So using the other idioms, we can take care of that part.
Okay. Yeah, they talk about the same thing here as well. Like, if that is one of the cons of the system, that if a message is huge and takes a lot of time to process, then it would hold up the whole partition. So, like for example, the message one in partition B from topic B from partition 0 was so big that it can never reach to partition 2, and it's holding up the whole partition from 2 to 4. So in that cases, it said that you should go for a different messaging system when basically the messages are um, basically huge to process. So they have specified that they can go for JMS, basically Java messaging service, which is, I think, Google's PubSub is the one based out of it, and the one we are talking about is like the AMQP, advanced messaging queue. So that was the this is the note basically. So it said that in situation where messages may be expensive to process and you want to parallelize processing on a message by message basis, and where ordering is not so important, the JMS AMQP style of message broker is preferable. On the other hand, in situation with high message throughput, where each message is fast to process and where message ordering is important, the log based approach works very well.
Yeah, so whatever Leon was asking, I mean, if we use the multiple consumer, then we cannot guarantee the order of the message.
Yeah, we cannot.
Yeah, and also the other point was that these log-based systems, they don't hide or delete the messages. So like if they would have that system that they can hide or delete the messages, then it would have been easier because then multiple consumers could have consumed from the same partition. But because their fundamental property is that anyone can read from wherever they want, because if there are situations when a new consumer want to read from the beginning, they support that. So that's why they don't have this hiding or deleting property. So then it becomes difficult to coordinate between multiple consumers consuming from same partition.
Yeah.
So in like we see the first consumer client, it consumed by two partition on topic in topic B, right? Partition 0 and partition 1. In that case, it already know. Oh, it keep track of partition 0, partition 1 index 2. Okay.
Yeah. Order guarantee is within the partition only.
Okay.
So one consumer can read from multiple partition, but multiple consumer cannot read from one partition.
Yes.
Mm.
So in the diagram also you can see like partition 0 and 1 are both read by the consumer client 1. But vice versa will not be possible.
And like multiple consumers can read from a same partition, but they have to be in a separate group.
Yeah. So then they are getting the replicas, right? In different group, they all are getting replicas of message. So then each will have their own offset, so they can independently read from those partitions.
What do you think about logical clock and offset? It's look like logic offset is some kind of logical clock within one partition. It look a bit similar to one port clock or something like this. Yes, each event we just increase a counter and we just increase an offset. There is some similarity. What do you think about it?
Similarity between what? Can you repeat? Sorry.
Between offset and logical clock. Logical clock like one port clock.
I think they're very similar. Yeah, logical clock is also keeping generally keeps an incremental number, and here offset is also this incremental number. I think, yeah, you're right. They seem similar. as per other skill
Yeah,
types.
and it looks like it track happens before. Yeah, it tracks happens before. We have happens before condition here.
Yeah.
Mm-hmm.
I have one more question about this scheme. Like before on the message broker, we push when a new message come, we push the message to the consumer, right? But in this case, it seems like the consumer keep the offset or the index of the next message. The consumer would pull the message. Is that
So this one is a pull model. So consumer pull the message.
okay? So when there's a new message come to the a partition, if the consumer not pulling it, then they're not gonna see it.
It will stay there in the queue.
I have a question here.
Yeah, but did not see it immediately until like the consumer pull it.
So, like as far as I was reading, like it's kind of a mix. So yeah, consumer will pull the message from the queue, but once it reaches the end, then it will stop pulling, because when there is no more message to consume, then it can't keep on pulling. There is nothing to consume, right? And then it's waste of request that it keeps on requesting from the topic that give me the message when there is nothing. So then in that situation, then it will stop, and then it waits for a notification. So then the topic will send a push notification to consumer that now there are new messages. Then the again system starts to pull. So until it the topic has the messages, the consumer will pull. Once there are no more messages, then the topic will push to notify that there are new messages, you can start consuming, and so like this.
Why we have to do that? Why can't we use long polling or something like that? Like, why are we waiting for a push notification? Why can't we do polling in long polling way?
Polling is that it will keep on asking that is there a message, is there a message, are you
Yeah,
saying
but
that?
if you do a long poll, it will wait for a certain period of time.
Yes, I mean, then yeah, consumer will have to keep on. So let's say then if you are increasing the wait time, that okay, there is no more message, now I will poll after 5 minutes. Okay, there is no more message, now I will poll after 15 minutes. Then
Yeah,
the problem is if the message comes, like you will poll me after 15 minutes and the message comes now, then like you will receive the message after 15 minutes because you will poll me after 15 minutes. So that's why I think an improvement is that as soon as, rather than giving the consumer headache of long polling after certain interval, you can just relax now and you have done your work. So relax, I will send you a notification when I have new message, then you can start polling again.
okay, so basically we can say that's a hybrid. It's neither pull nor push.
This is my understanding, yeah, like when I was reading, but
Maybe it depends, like with each system, like how if there are multiple log uh, message broker, they might be implemented in different ways. Like yeah, they could be using like pull, completely push, or both pull push, whatever makes sense to them. Okay. So we already talked about consumer offset. Uh, that it is this particular value over here, which tells the client from where to read, and why are we and why it is useful is, for example, this consumer client, the second one, let's say, uh, gets crashed, right? And it was reading from the offset 9. So now if we have, if since this is crash, will bring another consumer client right in its place, so that that can start consuming messages. So in that case, it should know where exactly it read last. So this consumer client information, this consumer offset, we will keep also in the message broker, so that message broker can tell the new consumer from where it should read. And I think somebody told the same thing. They said that you can keep it in a zookeeper, so that, in zookeeper, the advantage will be you can consumer can come directly contact the zookeeper and know from where it has to start reading, from which partition, right? So that's the advantage of using consumer offset, in order to have the crashed consumers replacement to perform accordingly. The next question that can come in mind is the disk space. Like, we are not deleting messages from here, right? And after a certain point in time, the disk might be full. Then what happens in such case? So in that case, what happens is, basically there is some it will start, like, basically the message broker, it will start overwriting the old messages in order to make use of the disk. So what happens is, basically, there will be messages getting produced, and because consumer cannot keep up with the rate at which producers are producing, and in that case, consumer will not be are not able to keep up, so the messages are flooding now, and then it has occupied the whole disk space. Now there could be a thing that only one of the consumer was slow and all other consumers were all caught up. Then we will not care about it. Either we can have some monitoring or alerting system, so that that is notified, that uh, the developers are notified that this consumer is not working well, and you might want to see what the issue is, so that and you can have a threshold value that now this consumer has lagged like 70% behind of what all messages are being produced in message broker, and then somebody can look up on it. Or else you can just let it fall behind and starts overriding the messages uh, on the disk in order to use it. So this is called as a circular buffer or circular queue, where you have all circular buffer or ring buffer. Basically, it seems like a circular queue where you have these messages, and now you start, this was the first message, and now you have completely filled your disk, so now the message will getting override. So now 8 will come here, 9 will come here, 10 will come here, so the old message will be overridden. So this is called ring buffer or circular buffer.
One question is on that the same topic, like when the consumer, how do consumer knows I'm reading slow?
No, consumer doesn't know. So consumer offset, so you can have some monitoring system, probably using consumer offset, and how many uh, messages are there in the message broker. If you can get those information, you can calculate that percentage of consumption for that consumer, and if it has lagged behind like with 70%, you can create an alert.
Yeah, okay, yeah.
So yeah, that was about this page. Yeah, other thing, that is the throughput. So the throughput is, so most messages system, what they do is they save everything in memory, right? And if needed, then they put it in disk. So if in memory size like the grows large, then they'll put it in the disk. So getting data from the memory is faster than the disk, we all know that. So right, so throughput depends on the amount of data that is on the disk, because that will be the response time that will take more time, right, in order to fetch the data from the disk. So the throughput of the system always depends on the amount of history retained, basically the amount of messages that are written on the disk. So this is the same topic, like when consumers cannot keep up with producers, and basically our disk has reached its limitation. So then the what you can do is, either you can have a threshold, and the other thing that it wrote that I couldn't understand and I have highlighted over here is that what this behavior of overriding the messages. So right over here we talked about this messages will be overridden. So they say that in that JMS or AMQP kind of messaging system, what they do is they the consumers use more resources, and they because messaging and they keep on accumulating messages, whereas in the log messaging system consumer don't do that. And I didn't understand why they said that, because uh, basically the behavior let me read it. This behavior also contrasts with traditional message brokers, where you need to be careful. Yeah, I didn't understand this line, where you need to be careful to delete any queues whose consumers have been shut down. Otherwise, they continue unnecessary accumulating messages and taking away memory from consumers that are still active. So I didn't understand how consumers will be taking away memory from other consumers in non-log message brokers. If somebody did understand this part, please uh, chime in. Should I pull this from book and maybe we can all read it together?
Yeah, wait, I'm not sure if you can share the book like
I'm
this.
not sharing the book, just copying some stuff. So I'll just copy paste here. So it was like in this point. So even if a consumer does fall too far behind and start missing messages, only the consumer is affected. It does not disrupt the service of other consumers. This fact is a big operational advantage. Yeah, I didn't understand this thing. So let's all take a minute to read it again.
So are they saying this, that basically in the traditional queues, because the messages are deleted, so now you have lost the message. But here, like because the messages are persisted, so you can like run experiments on that same set of messages with multiple consumers. So if one consumer was reading the message and it was that code was not properly written, and the messages it has consumed had some issues, the consumer had some issue, and you need to rewrite the consumer, you can easily do it, because the second consumer now can read the same messages from the beginning or wherever they want to. So like this makes it very easy to experiment and do stuff. Whereas if we had built a previous kind of a system where once someone has read the message, they are removed from the queue, then if you want to experiment with another consumer, that's not possible.
Yeah, that makes sense. But I don't know like whether they're Yeah, that is maybe that is what they're saying over here. But what are they trying to say over here? Basically,
I
that was.
think over the second one you highlight, let's say, okay, you have the consumer for this message queue, right? But right now, if the consumer is gone, you no longer need to that message queue because nobody use that queue, right? So it's better to remove that queue, or and then to save the memory. Because let's say you have two consumer interest in that queue, right? But now that two consumers are gone. So that nobody use the queue anymore. So that's why they want you to clean up and remove it.
Oh, but uh, hmm. Oh, but in like the log messaging, you can actually use that message broker because you can have a new consumer come up and use those messages.
Yeah, right.
But in the traditional ones, that's not the case.
Yeah.
Okay. Yeah, now I understood. Thanks.
But then in the which cases it we start deleting the queues, because they said you need to be carefully delete any queues, right? But now what is the like principle we will be using to delete those queues when no consumers are present at the time?
So, in all the traditional systems, they're saying that you have to be careful to delete queues.
Where we are not using logs.
No, we're using logs.
Mhm.
So there are two systems, right? One that we talked about, non-log ones, the AM, I forgot the name, whatever, JMS and AM QP, and then the other one, the log-based, the Apache Kafka one is the log-based.
No, I got confused. So then which one is the non-traditional if these are the traditional?
No, traditional one is the non-log ones. The one that we talked about where the messages were getting deleted. That is traditional system. The log system is not traditional.
So I'm saying in non-log based systems, we have to delete the message, right? This is talking about,
We have to delete the queues.
yeah, we have to delete the queues, yeah.
Yeah, that's
But when we are deleting it, when to that point, right, when we need to delete, because there is no consumers are using those queues. Now it is message broker kind of the you need to take a decision when he can go and delete, because the next point is taking away memory from consumer are still active, right? One way is if no consumers are present, we keep on accumulating a queue. At the end, nobody is using. When we can delete those kind of queues, when we can take that decision.
Yeah, I think when probably like my understanding is when the size of the queue is increasing and we have found out that the consumer is no more active. So then at particular threshold, we can say that delete this queue because the consumer of this queue is no more active. So rather than like wasting the memory, because since we are not using log-based system, so we are using memory. So the memory is limited. So then we can delete the messages. We can delete the queue.
okay. So let's make this replaying old message the last topic for today. And same too, we have already discussed. The reason why we came to log messaging approach is because we wanted our consumer to have the old messages to come into the same state if a new consumer is added, to bring that new consumer into the same state of the previous consumer. Or the other advantage that we get out of it is that if, for example, you have certain messages and you want, say for example, you had some code to add, there were, and let's say that those messages were numbers and we wanted to add those numbers, so we ran this code on those messages and that gave up the sum. Now we don't want to do the sum, we want to do the multiplication. So what we can do is we can just copy those messages onto a different place and then we can just run multiplication code on that, or whatever that we want to do. So that's the advantage we get. We can always replay our old messages and get new information out of it. So that's another advantage that we get. So that's that. And for this, we have actually finished the messaging part of it. And in the next session, we can talk about the data capture and how like messaging queue can be used over there.
Nice. Thank you so much, Shreya. So so let me stop recording and then we can